Hello everyone. Okay, this video I'm going to talk about the shear stress distribution in beam. Okay, but this video is conceptually not doing the calculation. Okay, so I just make an explanation why there is a stress distribution in a beam. Okay, in the lecture, we already know when we apply a load on the beam, there will be a stress distribution, okay, along the cross-section area of the beam, okay. And but in detail, in fact, okay, so there not only has a shear stress distribution at the web part, at the web part, okay. So this section is called web part, okay. In the top area, this portion and this portion, this is called flange. Okay. Okay, there is not only the shear stress distribution at the web part, also the shear stress distribution at the flange part. Okay, and the shear stress distribution at the flange part is gradually increase from the end to the center. Okay, that's this graph mean. The shear stress at the flange part is increased from the end to the center of the flange part. Okay. Okay, and right now I want to explain why there is stress distribution at the flange part. Okay, so I will use the top view. Okay, the top view means right now I'm looking at here. I'm looking at from this perspective. Okay, here's my eyes. Is here. Okay, here's my eye. I'm looking at the top view. Okay, top view. And now I focus on this part. Okay, I cut a small section at the edge of the eye beam, like for example, here. I cut a small section here. I cut a small section here. Okay, I cut a small section here. Okay, and then draw the graph, and then draw the top view graph at this section. Okay, this is a top view graph of this section. Okay, top view graph of this section. Okay. Okay, top view graph this section. Okay, at the top section, at this top section, we already know there will be a compression stress or tension stress. Okay, but for typical example, okay, let's assume the top section as under compression. At this top area, at this top section, at the flange part, we already know there's lots of compression stress or compression force at the flange part. Okay, so here I draw this arrow, blue arrow. This blue arrow is compression part. Okay, this blue arrow is the compression force. Okay. Okay, compression force. Okay, and on the top view, we cut a small section here. Okay, and also we can cut a small section here, and then we will compare the shear stress at this part and this part. Okay, let's begin. Okay, there is a difference. So you will see there will be a different shear stress at this position, okay. In this section, okay, in this section, small element, okay, we only has two compression force here. Okay, so in order to maintain a rigid body equilibrium, there must be a force here to resist the compression force. Okay, so this is called shear force. Okay, you must have shear force. Okay, from this element perspective, this force is called shear force. Okay, this shear force must be generated to resist the compression force to reach the rigid body equilibrium. Okay, that's this position. Okay, so let's look at when we move to the center part of the flange. Okay, we also cut a small section here. Okay, so in this section, we will have more compression force. Yeah, okay, because the compression force at the flange part is uniform distribution. Okay, so here I only have two non-compression force here, but here I have more compression force coming in. So I need to for this section, for this element, it need greater, larger shear force to resist the compression force here to reach the rigid body equilibrium. So the shear force here must be greater than the shear force here. Okay, when the shear, so you will see. So okay, when we walk from the end to the center, there is more and more compression force from the end to the center, of the flange. Okay, so the shear force must be gradually increased from the end to the center. Okay, because it must have the greater shear force or shear stress to resist the compression force. Okay, that's why there is a distribution of the shear force at the flange part, because the shear force is gradually increased from the end to the center. Okay, and because the cross-section area is the same. Okay, cross-section area is the same. Because cross-section area is the same. Cross-section area here is the same. It's same. Okay, so when we have larger and larger shear force, that's okay, and the cross-section area is the same, so that mean we'll have larger and larger shear stress from the end to the center. Okay, that's why we will have the shear stress distribution at the flange part. Okay, and then we will use the same concept to explain later shear stress distribution at the web. Okay, so here's the side view of the beam. Okay, so we only take the half, we only look at the upper section. Okay, because the lower section it's the same. Okay, it's the same thing. So we look at the upper section. So in the upper section, we also cut a section here and cut a section here. Okay, cut a section here. Okay, we will compare these two sections. Okay, similar concept in this section. This section is under the compression force and compression stress. So it must be generate shear force to reach the rigid body equilibrium. So it must be has general shear force to reach the rigid body equilibrium. Okay, so let's look at this section. This section again. Okay, so in this section, okay, we have a longer part. We have a longer section here. So at the bottom, because at the bottom, okay, or in this section, it undergo more compression stress than this. Okay, do you see that? Okay, on the left hand side is only under the compressing stress here. Okay, but at this part is undergo the compression stress here. Okay, so the right hand side at the bottom of the section, it's subject to more compression stress or compression force than the left. Okay, the right hand side is under the bottom of the right hand side experience much more compression force than the left hand side, than the bottom of the left hand side. Okay, so that's where it need to generate greater shear force. Okay, the right hand side must generate greater shear force compared to the left hand side to reach the rigid body equilibrium. Okay, so the same thing at the cross-section area. Cross-section area is the same. The left-hand side and right-hand side, the cross-section area is the same. So okay, so when the right-hand side has a large shear force, that means there has a large shear stress. Okay, so there is a shear stress distribution from the top to the center. Okay, like the shear stress distribution from the top to the center. Okay, that's why when we close to the center, there will be a large shear stress. At the top, we don't have much shear stress. Okay, because it doesn't have at the top. It doesn't experience. It does at the top. It doesn't experience much. It doesn't experience much the compression force. Okay, so that's why we will have the shear stress distribution from the top to the center of the web area. Okay, another thing I forgot to mention, and don't forget this concept. Okay. This concept is called shear force balance. Shear force balance. Okay, shear force balance. Okay, now let me draw this shear force balance. We have the shear force balance. Okay, the shear force balance. Okay, we have top. Okay, we have down. Okay, don't forget shear force balance. Okay, so in the top view, okay, we say there will be a shear force here to resist the compression force here. So there will be a shear force here. Okay, in order to reach the shear force balance, there must be a force here. Okay, so that's why the shear force draw in horizontal way here. You see the shear force at the flange part draw the horizontal way. Okay, and same thing here. Okay, at the web part, okay, we have a shear force here to resist the compression force here. Okay, so that's why we have for the shear force balance, we must have the shear force here. Okay, I think I should draw the different color. Okay, I think I should use different color better. Okay. So for at the web part, we have the shear stress here to resist the compression force here to reach each boundary equilibrium, and then also at the shear balance, we must be the shear force balance. There must be a force here to make the shear force balance. Okay, because if there is no shear force balance, the whole thing will keep rotating. Okay, so there must be a force here. Okay, so that's why the shear force arrow is drawing point down. Okay, you see the shear force arrow here is point down at the web part, and at the flange part is drawing the horizontal way. Okay, so that's the final thing I would remind you. Okay, it would generate shear force here, but and then the shear force balance, so it must be a general force. It also must be a shear force this way. Okay, there's a shear force generate here, but it must has the shear force generate in this way to reach the shear force balance. Okay, or the whole thing will keep rotating. Okay, so let's conceptually explain why there is a shear force distribution in the beam. I hope you can get more understanding about the shear force distribution in beam. Okay, it also comes the rigid body equilibrium and the shear force balance, and also you need to know the concept. Okay, there is a when we apply a load in beam, there is the tension force and compression force generate, and then you use this force to discuss in each section you will reach the conclusion that there must be a shear force distribution at the flange part and the web part. Okay, so here is the video. Okay, hope you can understand. Okay, we'll see you next video. Bye bye. Hi, not here.